So let's do another example here. Let's suppose that we've got out in deep space, we've got a long massless rope or something, and we got two astronauts holding on to it. Okay, and one at each end here, and let's go ahead and put these astronauts, I guess, in a spacesuit so they don't suffocate. Okay, and so let's say that it's rotating around its center of mass here. These two astronauts holding onto the end of this long thing, and they're going around at 2.11 radians per second. Let's say that each astronaut has the same mass, okay, and let's say this is 425 kilograms, okay. Now that's not the mass of the astronaut per se, that's the mass of the astronaut plus the spacesuit. And that's really very close to the actual mass of an astronaut in spacesuit. They are very, very heavy. There's no way you can actually stand up in one of these things on Earth. And so, weightless environment, you're okay. But, it doesn't work here on Earth. In fact, when they test and practice, they have a giant underwater tank in Houston. They practice doing spacewalks in, and they put on their spacesuit, and they can't move. A crane has to pick them up and lower them into the giant water tank in order for them to float and move around. Okay, so let's say that initially they are some distance d naught of 31 meters apart. Now, what's going to happen is one of these astronauts is going to pull forward, climb forward until the pair of them are closer together. Okay, so now we're going to say that the D is going to be 16 meters. And so what I want to know is they're still going to be rotating around the center of mass, so I want to know what is the final angular velocity. Okay, so what we do is we say that initial angular momentum equals final angular momentum. So the initial angular momentum will be the I initial omega naught. The final angular momentum will be the I final omega. Okay, so omega is going to be I initial omega naught over I final. So all we got to do is find the I's. So if you imagine these two astronauts right here, okay, then there's some distance d apart, okay, so we'll call r 1/2 of d, and so the I is going to be mr squared. They both have the same mass, and 2. Okay, so it'll be just 2 mr squared. Okay, and so that means that I initial is going to be 2 mr naught squared, and so I final will be 2 mr final squared. Okay, because everything else stays the same. And so that means we would say 2 mr r naught squared, omega naught squared, omega naught, okay, equals 2 mr squared omega. So that would be, that right there is my L initial, there is my L final right here. Okay, so initial equals L final. So we just do a little bit of algebra in here, and we find that omega is going to be equal to 2 mr naught squared omega naught divided by 2 mr squared omega. The 2's cancel, the m's cancel, and sorry, no omega down there. Okay, so it's going to be r naught squared omega naught over r squared, and so that comes out to be r naught is going to be half of the initial distance, so that would be 15.5 meters squared times the initial 2.11 radians per second, and then you divide by the final. They're 16 apart, so that means that r is 8 meters. Okay, you plug in numbers, and what you get is that omega is 7.92 radians per second. Okay, now remember we said omega naught was 2.11 radians per second. So as they got closer together, they sped up. Well, what would have happened if they had actually gotten farther apart? They would have slowed down. In fact, that's actually one of the strategies that's used in launching a rocket, is when you launch a rocket or a satellite, to stabilize it, they will sometimes spin. Okay, now if you de-spin, what you do is in the satellite, you have these heavy weights, you roll out the heavy weights on long cables here, and so that increases the moment of inertia, which slows the rotation rate of the satellite. Okay, so next question would be the change in kinetic energy. So the initial kinetic energy would be 1/2 the initial 2m r naught squared times omega naught squared, and the final kinetic energy be 1/2 times 2m r squared omega squared. Okay, the 2's all cancel. You plug in the numbers here. If you plug in the numbers, you get 455 kilojoules, and you plug in the numbers at the end, 1710 kilojoules. So the change in kinetic energy was an increase in 1260 kilojoules. Well, wow, where did the energy come from? How did we get this increase in energy here with these two astronauts? Well, remember, as this thing is spinning around, you got a centripetal force that's pulling inwards on the astronauts. That means the astronauts equal and opposite force. It feels like they're being pulled this way, that so-called centrifugal force, which is really a pseudo force. In order for this astronaut to pull this way, they're pulling themselves forward against that force. And the farther in they pull, the bigger that force would tend to be, and so the harder they have to work. And so what happens is that in the end, that they are having to exert, a lot of calories. They're having to use biochemical energy to pull themselves forward against this apparent weight. And so that is like climbing uphill or pulling yourself up a rope, ladder or something. You're doing work, and that work is going into the rotational kinetic energy. So that's why the final kinetic energy, in this case, the final kinetic energy was greater than the initial kinetic energy. This is why really whenever I ask, what's the change in kinetic energy, you should really give the sign plus or minus to indicate whether you're increasing or decreasing kinetic energy.